All right, so today we are going to be talking about matching in analog networks or analog components. And so I'm going to draw a circuit. And then we are going to talk about what parts of this circuit require matching. So here is our circuit of interest. Ooh. Almost done drawing. Okay. This line through just means these gates are tied together. Let's call this 1 and 2, 3 and 4, 5, 6, 7, demo. So, anybody know what this is? Seems pretty easy if you recognize it. Anybody? This is an op amp. This is what we're going to design in this class. We might make it slightly more complicated than this, but this is literally a multi-stage op amp where this guy right here is our reference current generator. So we have current mirror right here, which is serving as our tail current for our differential bit. We have our single stage op amp phase right here, Then we have this compensation bit right here, which is what's going to allow us to drive a resistance with our output stage over here. And we'll talk about how all that stuff links together and how it works and all that kind of jazz over the next several weeks. But for this thing to work correctly, we have to have matching in our differential phase, right? Which is our single stage op amp that I've drawn the big circle in the middle, right? So if transistor M1 and transistor M2 are not perfectly matched, we are not going to get the behavior that we expect. If transistor M3 and transistor M4 are not perfectly matched, this is not going to behave correctly. We could bias this thing with resistors as well, which would in turn have to be matched, et cetera, et cetera, et cetera, okay? So why is matching so important? Well, matching between components in analog circuits is critically important because process variations during fabrications can drastically change the accuracy of the things that we're actually laying out, our structures and stuff like that, okay? So we are going to talk about simple matching techniques today, and we're going to limit this to generic two-terminal elements for today only to wrap our head around what matching looks like. And then we will expand this to include three-terminal devices like transistors and all that kind of stuff after we get into more detail about how transistors are laid out. Okay? So our matching method number one is what I'm going to call interdigitation. So let's say that we have to match two components. A and B, where these components could be resistors, capacitors, transistors, or anything. What we're going to do is we're going to split component A and component B into four smaller components. A1 through A4 and B1 through B4. Okay. So a conventional layout would look something like this. So here is A1, A2, A3, A4, and I'm just going to tie these guys together like so. So we've made a little serpentine pattern here by splitting our component A up into four identical components. Over here on the right-hand side, let's do the exact same thing to B. So if there is a 1% process variation from left to right, then A total would be A1 plus A2 plus A3 plus A4, which would be A1 plus 1.01 A1 plus 1.02 A1 plus 1.03 A1. So effectively, the further we move to the right, the more variation we get. If we add all these numbers together, we find that A total is 1.015 times A, which was our original component value before we split it up. Similarly, for B, we would have B1 plus B2 plus B3 plus B4, which is going to look like 1.04 A1 plus 1.05 A1 plus 1.06 A1 plus 1.07 A1 Hold on. So sorry. Why I'm saying hold on here is because I'm concerned about, so the intermediate step here I know is correct, but 1 plus, okay, let's do this in a slightly different way here. So that 1.015, I think, is the average value. So what we would have here is 1 plus 1.01 plus 1.02 plus 1.03. So that's going to look like 4 point, let's see, 1 plus 2 plus 3 is 6. So 4.06 A1. And then we divide that by the 4, I think. And this is how we would get 1.015 A total. So I was missing that intermediate step, and I wanted to make sure you guys understood where the math came from. So from here, this is going to look like 4 point, let's see, so 9, 15, 22. A1, which would look like 1.055 A. And if components A and B are supposed to be matched, this is not particularly good matching, right? So they are, component A is a little bit more than its expected value, which is going to happen with process variations, but component B is significantly more than the expected value because the process variation increased linearly from left to right, okay? So interdigitation of the components means, so let's write here, standard. If we were to interdigitate the components, which I'll just call it ID, we would have something like this. So I'm going to lay out my 8 blocks. Identical things. 3, 6, 7, and 8. Well, let's say that this is A1, this is B1, this is A2, this is B2, this is A3, B3, A4, and B4. And we wire them up. Like this. So wiring our components together is significantly more complex, right? But for that same process variation, so again, we'll assume 1% from left to right, A total would be A1 plus 1.02 A1 plus 1.04 A1 plus 1.06 A1. Looks like 2 plus 4 plus 6 is 4.12 A1. And so A total is 1.03 that we're expecting. So it's still a little bit larger because of the process variation. We look at B, we're going to have 1.01 A1 plus 1.03 A1 plus 1.05 A1 I'm sorry, 1.07 A1. Add those things there, so 4 plus 12 is 16, so 4.16 A1, meaning that B is just 1.04 A, and we see that we have better matching, right? The overall component values are closer to each other, and we could do other interdigitation schemes, okay? So we could do A1, A2, B1, B2, A2, or excuse me, A3, A4, B3, B4, etc. And we would find that we'll also get better matching than not interdigitating, but we're never going to get anything better than this, where we're literally alternating every other element, okay? So this is the interdigitation method, and this one is pretty straightforward to understand, okay? Now, let's talk about method 2, which is the common centroid matching methodology. Right. So I'm going to lay out our 8 sub-elements here. Six, 7, and 8. Okay. So in a common centroid layout, we make sure that our pieces are symmetrical about the common centroid. So the common centroid is just the point in the geometric center of this array. Right here. 4 elements to the left, 4 elements to the right, assuming everything here is evenly spaced. So what we would do is if we put A1 on the left-hand side over here, let's put A4 all the way to the right-hand side. If we put A2 as this 4th sub-element, A3 needs to be the 5th sub-element so that A1 and A4 are equidistant from the common centroid. A2 and A3 are equidistant from the common centroid. And then we can put B1 here, which means we'll need to put B4 here and B2 here, which means we'll need to put B3 here. And we could mix and match these around as long as we're equidistant from that center point, we are doing it correctly, okay? So If we wired this thing up, it's going to be one little exercise here. So again, assuming 1% process variation from left to right, we'd find that our A component is going to look like A1 by itself. A2 is 1.03 A1. A3 is 1.04 A1. And then A4 is 1.07 A1. So that's going to be 4 point, let's see, 3 plus 4 plus 7 is 4.14. A1. And thus a total is 1.035, our nominal value of A. B total, so we're going to have B1, which is 1.01 A1, B2, which is 1.02 A1, B3, so let's see, so that's 0.3, 0.4, 1.05, 0.06, and so 1 plus 2 is 3, plus 5 is 8, plus 6 is 14. We have 4.14 A1 yet again, meaning that B total has the exact same value as A total. So even though we have this process variation linearly moving across here, we can get perfectly matched components. What's really great about a common centroid layout is that it is not in any way, shape, or form restricted to a single dimension. So we can do common centroid arrays on our 2D plane that will allow us to do perfect matching. So in a 2D space, let's say that we had something like this. Our common centroid would be this middle point. There are 4 to the left, 4 to the right, 4 above, 4 below, right? If we put A1 here, we'd need to put A4 here. We put A, do it here, A2 here, we can put A3 here. If B1 is here, B4 needs to be here. If B2 is here, B3 needs to be here. And we have perfect matching yet again. And any way that we do this, as long as all of our A components are equidistant from the center point and our B components are equidistant, we're good to go, okay? So just as an exercise here, let's say that we have 3 elements, A, B, and C, that we've split up. If I put an A right here, where does the matching A have to go? Gavin, where do you think it goes? Right here. I agree. If I put a B here, somebody else, where does the second B have to go?
Mirror it across the other side. If you put your Centroid to steer control.
It's probably easy just to like, you could just put a dot. Just mirror it.
Yeah, that's the exact, that's literally what we're doing.
Put the Centroid in, put a mirror across it, just.
Yeah, no, I agree wholeheartedly. This is not hard. That being said, other times I have taught this class, students have struggled with this concept, which is why we're doing this, I believe, extraordinarily simple exercise. It seems very, very logical. Effectively, how I treat this is I take a line from the center point of my element. I go through the centroid, and wherever I hit is where the other one needs to go. I just keep on going. So if I put C here, obviously I need to have a, if I put a C in the bottom left, the corresponding C has to be in the top right. Like so. If I put a B here, I need a B here. If I put here, then I have to have a C here. If I put an A here, then I have to have an A here. As long as I have pairs that are equidistant apart, I have a common centroid layout. This is the best and most efficient matching that I can do to ensure that my elements' values are as close to each other as they can possibly be. Now, that being said, the interconnections here can be a nightmare, right? The more complex we make this, the harder it is to lay this thing out and physically connect the sub-elements to each other without introducing things like parasitic resistances, parasitic capacitances, and all that kind of stuff. We have to have multiple metal layers in order to even attempt this, because if I have a single metal layer, if I cross over getting to another element, those metals touch, and now everything is connected together instead of just A to A, B to B, et cetera, et cetera. So for something like this, 3 to 5 metal layers would be the easiest way to do this. 2, I think, would be impossible. Right, so that's just something to think about here. And this is, again, dealing with a trade-off between cost and performance, right? The performance of having these elements perfectly matched gives us exactly what we're looking for. We get effectively ideal behavior, but that increases layout complexity and therefore fabrication cost. Okay, so this is 2 element layouts. Now, Monday, we'll start talking about the layout of transistors and all that kind of stuff. And I will show you common centroid for matched transistors. And it is a funky looking thing, as you can imagine, when you have a 3-terminal device and you need to make sure your gates satisfy the common centroid, your drains satisfy the common centroid, and your sources satisfy the common centroid simultaneously. Yeah, it gets wonky fast. So All right, that's enough out of me. You guys enjoy the rest of your Friday.
Question.
Yes, sir.
What about transportation?
So that's why in a 2D space like this, common centroid is still the best thing, because if you have some point, if a process variation changes across a diagonal or something like that, this is still going to satisfy it. Yeah, so interdigitation is great for a linear array. Common centroid can be applied in both the X and Y directions, which is why it works so great. It does not matter. And I'll have to find, I don't have the notes here, but I did something effectively to illustrate that. I want to say in 335, like 2 years ago. Or maybe it was 336 2 years ago, to effectively show it does not matter if your process misalignment is from the left or the right, or top to bottom, or diagonally across. The centroid layout effectively negates all of those effects. Pretty fantastic, but I'll have to remember where I put that quick little thing. Like I told you guys to it, because I think it was the year that you took it, kind of as an aside that took about 10 minutes of just when we were doing some electric stuff about, this is something you might want to think about. And then God only knows where I put those notes. So anyway.
I'm about to find out if you're doing this.
I think I would have done it in 330, probably 336 at some point. And it would have been part of a larger lecture. So good luck looking through those 25-ish videos.